Thanksgiving fast approaches, and in the Boscher family, that means Grandma's black bottom pie, a 3-layered custard wonder of the world. Of course, I'm sharing a recipe from Southern Kitchen rather than Grandma's prize recipe. That's a closely guarded secret. I inherited the cookbook, and Grandma still says it isn't the complete recipe. This recipe from Southern Kitchen yields 2 pies. If I know the yield of the recipe, I can actually figure out how much I need of any of the ingredients based on that yield. Suppose I want to make a complete recipe of 2 pies. If I'm worried about having enough eggs, I can look through the recipe to find out how many I need. Turns out 3 eggs is enough for 2 pies. But I can also figure out how many pies I can make based on the ingredient that I have least of. Suppose I have 3 packs of gelatin. Since each recipe takes 1.5 packs of gelatin, if I have 3 packs of gelatin, I have enough for 2 recipes, or 4 pies. This is a recipe that deserves having 4 pies made. And of course, I can compare the amount of each of the recipes I can make based on the ratio of ingredients and how much I have. So if I have a bottle of rum, that's more than enough for a recipe. But if I only have 3 eggs, I'd say that the eggs are a limiting ingredient, only allowing me to make 2 recipes regardless of how much rum I have. All that leftover rum will be just left over. Turns out if you aren't careful with all that leftover rum, you might need some aspirin. But I've got some willows in the back, Salix discolor, with some salicylic acid in the bark. And I've got some vinegar in the cupboard with some acetic acid, and I've got Grandma's recipe for acetylsalicylic acid, the more fun way to say aspirin. Turns out I can use this chemical equation in the same way I used the recipe in baking. There's a good chance that you know how to do this already, you just didn't know that you knew how to do this. If I want 6 aspirin molecules, or acetylsalicylic acid, and the recipe says I only get 1 aspirin per recipe, I know, for example, that I need to do the recipe 6 times, and that each time I will use a vinegar molecule for a total of 6 vinegar molecules. And that ratio works in moles too. If I have a mole of salicylic acid and plenty of vinegar, I can make a mole of aspirin. In fact, we can set up any relationship between molecules in a reaction as a conversion factor. The coefficients in the chemical equation go in front of the unit, either molecules or moles of a specific substance. The conversion can give us true statements about different reactants or products based on any other component in that reaction. Those ratios can even be used to compare amounts to a limiting amount. Anything that's above the ratio expected won't yield product. When we're talking about these ratios in chemistry, we use the term stoichiometry, from the Greek for element and meter. And when we have real reaction conditions, just like when we're baking, we usually have extra of something. We say that we have excess. The thing that we have the least of compared to the recipe is considered limiting. This doesn't mean that it's the lowest amount of something. If we have 2 times as much of something as everything else, but the recipe calls for 6 times as much, it's still going to be the limiting ingredient. We can only use ratios of moles or molecules to predict relative amounts of materials, which means that we always need to do reaction calculations in terms of moles. However, we can't measure moles, either in reactants or in products. We can only measure things like volume, mass, and concentration. But we already know how to convert between mass and moles, molecular weight. And we know that we can use the density of a pure substance to convert between volume and mass. Even concentrations we can now use to convert between a volume of a solution and moles in solution. Since we can do all of those conversions, we can easily convert between a measurement for one component of a chemical equation and a measurement of another component. Let's work through a few examples. First, a straightforward conversion from moles to moles. This reaction is the same one that we used in the Haber-Bosch process that we balanced in the last section. If we know moles of N2 and we want to determine the moles of NH3, ammonia, we can set up the problem as a dimensional analysis problem, as we've done before. So what do you need on top? We need moles of ammonia on top and moles of N2 on the bottom. The coefficients come along with the unit labels, so we have 2 moles of ammonia over 1 mole of N2 for a total of 2 moles of ammonia. But we don't need to start in moles to make these conversions. We just need to do the conversion part in moles. Suppose we have a given mass of a substance, here potassium phosphate, that we want to react. If we know the reaction stoichiometry from a balanced reaction, we can convert between moles of reaction components, but not between masses, since the masses have nothing to do with the reaction ratios. So we need to set up the problem in two parts. First, we get moles of potassium phosphate. Then, we get to moles of calcium phosphate based on the stoichiometric ratio. So first, what do we need on the top and the bottom of the conversion grams to moles for potassium phosphate? Moles over grams is the inverse of molar mass or molecular weight, so we'll have to figure that out. For a review, see if you can figure out the molecular weight of potassium phosphate to 1 decimal place precision. We should have 1 mole of potassium phosphate over 212.3 grams of potassium phosphate, which we get by adding up the atomic weights of each component. 3 times 39 for 0.1 for potassium, 31.0 for phosphorus, and 3 times 16.0 for oxygen. Altogether, this gives us about 15 millimoles of potassium phosphate. We should really only keep one significant figure if we're going to report that number, but since we're going to continue on with our calculation, we'll keep the significant figure part for later. The next conversion is from potassium phosphate to calcium phosphate. We just use the mole-to-mole ratio. We can ignore the milli prefix and carry it through to the product, or we can use the ratio as millimoles to millimoles. It works out the same either way. And we end up with 8 millimoles of calcium chloride. Technically, this already gives us a much. Moles measures quantity, as does mass. If we felt we needed to convert to mass, we could do that too. We just need to multiply by the molecular weight. An example that you might need to do a little bit of looking up for. If we're given 1 gallon of ethanol, we don't need to know all of the conversion factor values that we might possibly need, but we should absolutely know what conversion factors we might need to go and look up. So first, see if you can identify the steps that you need to go through to get a how much, either mass, moles, or even volume, a carbon dioxide answer. If you get stuck, refer back 2 slides rather than continuing on. Again, how much can be moles, mass, or volume. But we know that the stoichiometric conversion must be done in moles, so we've got to shoot for that. We know that we can't convert gallons of ethanol to moles carbon dioxide directly, so we'll have to work our way backwards. So what can we convert into moles carbon dioxide? Get moles carbon dioxide, we're probably going to be in moles of another reactant, and since we're looking at ethanol, that's probably the moles we need. We can do this with the reaction stoichiometry to convert between moles ethanol and moles carbon dioxide, which we already have from the balanced equation. If we have moles of ethanol, we can actually get back to mass of ethanol from the molecular weight, which you can find using the molecular formula and the periodic table, or Google. We can get back from the mass of ethanol, grams of ethanol, to volume using density. Most densities aren't reported across both customary and metric systems, so I actually have to go back to volume in 2 hops, first to liters or milliliters, and then to gallons. You'll probably need to look up density of ethanol and the gallon to liters conversion. That's okay. This is about understanding what you need to look up and how to set up a problem. It's not about pretending that Wikipedia doesn't exist. You could envision going directly between liters of ethanol and moles of ethanol as well, using the molarity of pure ethanol at room temperature. If you are the choose your own adventure type, by all means, that's a creative and correct solution. But it will be hard to find a correct value. That one is not in Wikipedia. Anyway, look up the necessary conversions and see if you can figure out how many moles of carbon dioxide are produced by 1 gallon of ethanol. Here's how I set up the problem. I chose to find a gallons to milliliters conversion because I knew that ethanol density would be in grams per milliliter. It's not a problem to add a liter to milliliter conversion as well if you found a grams to liter conversion. After all the unit conversions, we end up with about 100 moles of carbon dioxide to one significant figure, which is about what we started with. If we wanted to go one step further to the mass of carbon dioxide, we'd want to hold off on rounding to the number of moles, which calculated closer to 130 moles, and multiply by the molar mass of carbon dioxide, which is about 44 grams per mole. In that case, we'd end up with about 6 grams of carbon dioxide per gallon, or about 13 pounds. To give this number some context, if ethanol is used, the gas mileage of a normal car is about 2/3 of what you'd get for gas. An average new car probably gets a little bit more than 30 miles per gallon, but SUVs and trucks generally would get a little less. So we're going to use 30 miles per gallon as a middle of the line guess. So a gallon of ethanol probably gives about 20 miles per gallon fuel efficiency. If we go 20 miles, that would be 1 gallon, which we found produces about 100 moles or 6 kilograms of carbon dioxide. It would take you about a week to generate this much carbon dioxide just by breathing, for reference. In addition to performing calculations in idealized reactions where everything gets converted to product, we can also perform calculations based on stoichiometry to find out which reactant, also called a reagent, is limiting. Before I had kids, I would arrange science experiments with my nieces. This is one of my favorite ones. A careful eye may recognize the leftmost reactant as vinegar, so this is the baking soda and vinegar experiment. But my nieces, probably 3 and 5 at the time, quickly realized that 1 liter of vinegar that I put into a big Erlenmeyer flask could only react with baking soda for so long before the reaction stopped. The vinegar was the limiting reagent, so they needed to add more if they wanted any extra of the baking soda to react. After a while, the extra vinegar wouldn't do anything either, and they needed to go back and start adding baking soda again. This is the children's version of limiting reagents. Once something reacts completely, it's gone. It doesn't matter how much of the other components we need. We can quantify this by calculating the number of moles for each reactant. So I did the calculation. A liter of 5% acetic acid, which is white vinegar's concentration, is about 0.9 moles of acetic acid. Since baking soda reacts with acetic acid in a 1-to-1 ratio, anything above 0.9 moles of baking soda would be excess, and anything below would be limiting, meaning some vinegar would be left behind. It's important to note that these calculations are always based on stoichiometry. If we needed twice as much baking soda to react, the cutoff between excess and limiting would be twice as high. We don't only compare the amounts of reactants to see which is limiting and which is excess. We can also make calculations of yield, how much product is actually produced, based on limiting reagents. For our example of aspirin synthesis, we always react excess inexpensive acetic acid with salicylic acid, which is more expensive. That means salicylic acid is limiting. If salicylic acid is limiting, in theory, all of it should react. So we can use the moles of the limiting reagent, again, always the limiting reagent, to convert to an expected amount of moles of the product. This is the theoretical yield. We can express the theoretical yield in moles or grams, but it's typically reported in grams. That's because we'll also measure the actual yield of a reaction, which we can do with a scale measuring grams. This is from an actual experiment that we'd run. For many actual experiments we run, we'd also report the percent yield, the actual yield divided by the theoretical yield multiplied by 100% to express as a percent. Percent yield should always be less than 100%, since you should always get less than is theoretically possible, but ideally as near to 100% as possible. That indicates a good reaction in many cases. A percent yield over 100% usually means that water was measured along with the product. See if you can identify the theoretical yield, actual yield, and percent yield if 2.76 grams of salicylic acid, which has a molecular weight of about 138 grams per mole, reacts with excess acetic acid to yield 2.70 grams of acetylsalicylic acid at about 180 grams per mole. Actual yield is given, 2.70 grams of acetylsalicylic acid. Theoretical yield would be obtained by dividing 2.76 by 138 grams per mole to get moles of salicylic acid, then multiplying by the 1-to-1 ratio of acetylsalicylic acid to salicylic acid from the reaction stoichiometry, and then multiplying by 180 grams per mole to get a theoretical yield of 3.6 grams. Notice that this is higher than the mass of salicylic acid that goes in. That sometimes throws people, but remember, it has a higher molecular weight, so the same number of moles should have more mass. The percent yield is going to be the 2.70 actual yield that we got over the 3.60 that we could theoretically get, which is 0.75 or 75%. Not every reaction can give 100% yield, even if performed perfectly with a lot of excess reactant. But for many reactions, particularly certain types of redox reactions and acid-base reactions, the reaction can go to completion or at least near to completion with very little excess. This is useful because it allows us to react a known amount of reagent with an unknown amount of another reagent to figure out its concentration. This process is often performed by adding one reagent slowly and measuring the volume slowly, and it's called a titration. We'll do some titrations in lab, but we'll get a jump on some of the vocabulary now. First, the equipment that we use is a large tube with graduated markings and an on-off valve, which you can see in the figure on the right. The tube is called burette, and there are special clamps that we use to hold it level, called burette clamps. The solution that we put into the burette typically has a known concentration of the reagent, and we call it the titrant. We slowly add that titrant to another solution that contains the analyte, the thing we want to measure. We can titrate solids technically, but we usually dissolve them first to make sure the titrant and analyte can readily mix. Otherwise, it takes a lot of time for the solid to dissolve and eventually react. When the molar ratios are such that there's sufficient titrant to react the analyte, we really reach what we call the equivalence point. In an acid-base titration, this tends to be when there's a 1-to-1 ratio of acid-base. Sodium hydroxide is a very common titrant, and so the equivalence point allows us to measure the amount of the analyte that goes with it, which in this case is the HCl, the hydrochloric acid. In acid-base reactions, we could use a pH probe to measure the amount of H+ directly, but it's not as accurate as the result we could get from a titration. We could also use a pH probe to give us the equivalence point. There's a change in the graph that indicates the equivalence point, but it's often much easier to use an indicator, a molecule that changes color in different conditions. The molecule shown is phenolphthalein, which turns from clear to pink in basic solutions. As soon as the equivalence point is passed, excess base builds up and turns the phenolphthalein pink. When you use an indicator, the actual change we see is the endpoint, not the equivalence point. We try to make sure that these are as close as possible by adding only a small amount of indicator and asking someone who's not red-green colorblind to look at our titration. Certain precipitations can also proceed more or less to completion. Since we can separate out solid and measure the mass, this form of analysis, called gravimetric analysis, can give us access to concentrations of components that aren't available by titration. The reaction shown uses the known concentrations of silver nitrate in order to figure out how much chloride is in solution by precipitating out this silver chloride.